welcome everyone, and I'm very happy to be introducing Alexie Leauthaud. Actually, I'm not sure if I confirmed that this is the correct way of pronouncing your name, Alexie, so you might.
It's very close. Well done.
Thank you. So Alexie is a world expert on many topics in galaxy formation and cosmology, primarily using the empirical tool of gravitational lensing. So she's made many fundamental contributions to our understanding of the so-called GalaxyHalo Connection, the connection between dark matter halos and the properties of the galaxies they host. I've known her for many years. We're postdoctoral fellows at the same time at Berkeley. At the time she was a Chamberlain Fellow at Lawrence Berkeley National Lab. And after that, she spent several years in Japan at the IPMEU in Tokyo, including as a faculty member there before moving to our current faculty position at UC Santa Cruz. And she's been very successful already, as I think a slide hints at. She's been awarded a number of early career awards, including the Sloan Packard and DOE early career awards. So we're very fortunate to have her tell her about some of our recent results today. So thank you, Alexie. Looking forward to it.
Thanks so much, Claude-André. And yes, I'd love to visit in the future when it's possible. That would be really fun. All right, I'm going to tell you today about some recent work regarding galaxies, dark matter, both in terms of cosmology, but also in terms of some galaxy formation. So just to set the stage, dark matter is the dominant component of our universe, and the spatial distribution of dark matter and its evolution with time, which is encoded in the power spectrum, contains a great deal of information about the cosmology of our universe, and as such, we'd like to measure it and probe this component. Now, in reality, when we look at the universe, this video sometimes works, we see the galaxies over here. What we'd really like to probe is the dark matter component shown over here on the right-hand side. The dark matter component is much more difficult to probe. I'm going to tell you about gravitational lensing, a technique that I use to make the connection between the galaxies that we see in optical surveys and the underlying dark matter. This connection, also termed the GalaxyHalo Connection, tells us both about cosmology, in particular the growth history, can tell us about possibility to modify gravity, dark matter models. It also informs us about structural formation. We can use this connection to try to see if there are baryonic effects of the dark matter, baryonic effects on the dark matter. We can talk about the edges of halos, assembly bias, and other such topics. And then understanding this connection also helps us understand the formation of galaxies, in particular by trying to probe and understand their dark matter content. The technique that I primarily use is gravitational lensing. And I have this little video. This is the essence of the technique. So in the absence of matter, light travels in a straight line. But with a very large overdensity, such as a cluster shown here, light is bent according to the laws of general relativity. And we see these distant arcs. These are background galaxies whose light has been stretched to form these spectacular arcs. And this is the strong gravitational lensing regime. And studying these arcs tells us about the presence of dark matter. And so this is one of the handles we have on the amount of dark matter in the universe. I actually study a different regime called weak gravitational lensing, which enables us to study any kind of galaxy and dark matter distributions out to much larger radii than strong gravitational lensing. Before I tell you about that, let me define a little bit of terminology here. So this is a dark matter halo. We know that galaxies are embedded in these dark matter halos. The galaxies that live at the center of these halos are central galaxies. That's self-evident from the term. And then other satellites that orbit around in these dark matter halos are called satellite galaxies. Furthermore, some other terminology I will use are in situ stars and ex situ stars. In situ stars are stars that are formed within, for example, the central galaxy. In this halo, they're formed directly in place, hence the word in situ. Ex situ stars, however, are stars that are formed in these satellite galaxies and have been brought onto the central galaxy via merging or tidal disruption. And so these stars were formed elsewhere and were brought in by these accretion processes. And this will be relevant for one of the aspects of my talk. The gravitational lensing technique that I will use in particular is called galaxy-galaxy lensing. And what we do is we select a sample of foreground galaxies. This could be your favorite galaxy, could be sample of AGN, could be early type galaxies. And we create a series of radial bins that are usually circular and that extend from a few hundred kpc out to 10, 30, 40 megaparsecs. Just depends on your data set. And so we create these bins and we measure the average tangential shear in each of these radial bins. And that tells us about the foreground matter distribution around these galaxies. And this is how we can directly probe the dark matter content of these galaxies. These are the kind of figures that I will often be showing you. This is a quantity called delta sigma. You can think of this as an excess surface mass density. This is total matter, so including dark matter, but also baryons, but often dominated by the dark matter component. And then on the x-axis here, I'm going to be showing you R. And so this is the distance from the sample of galaxies that we are studying. Again, ranging from a few hundred kpc out to tens of megaparsecs. And then the amplitude of this signal basically tells you about halo mass. So we're going to look at some of these amplitudes changing. And if the amplitude goes up, you live in a more massive dark matter halo. If the amplitude goes down, you live in a less dark matter halo. One minor point to mention here is that we do not do this for an individual galaxy basis in general, unless we have a very massive galaxy cluster. Instead, we stack, we study thousands to tens of thousands of galaxies stacked together to measure their average halo properties. But lensing surveys are becoming very large and the signal to noise is becoming very good. And so you'll see that these signals are starting to become very well constrained. These have error bars, for example, here, even these red ones. So I'm going to tell you about 4 different things. My point 4 is just a few slides, it'll be very short. One is called lensing is low. Then I'll tell you about the relationship between galaxy size and dark matter halo mass. Some new work we've been doing, thinking about the scatter between galaxies and halos. And then finally, just an advertisement about a new effort that we are starting. So one of the things I've worked on is combinations of galaxy-galaxy lensing, the technique that I mentioned earlier, and galaxy clustering. This is shown on the right-hand side. Galaxy clustering is the 2-point correlation function between galaxies. And it's been measured with very high precision from surveys that try to probe the baryon oscillation, baryon acoustic oscillation peak, such as BOSS and soon DESI. And when you combine these 2 probes, there are some interesting things that you can test. Primarily, you can test the growth history of the universe as encoded by, here I'm showing it's called the S8 parameter. You can think of it as a combination of omega m, the dark matter content of the universe, and sigma 8, how the power spectrum has grown over time. And probing this is of great interest as a complement to the expansion history, for example, as probed through H0. We can also test modified gravity models and things like baryonic effects and assembly bias and many other different things. So there's a great deal of interest in combining these kinds of different probes. And then in 2016, I published this paper, which took clustering from the baryon oscillation spectroscopic survey BOSS and tried to combine it with gravitational lensing. I actually started this as a postdoc when I was at LBNL when Claude Ng was in Berkeley. It took many, many years to finish this. So just, for those of you out there who are struggling on white whale projects, this was my white whale. And I struggled for many years because I could never get the data to fit. So we went through lots of different models and tried lots of different things that never worked. So in the end, I published this result. This is showing that these are models that fit the clustering. And there's different models. I don't want to go into the details, but these are the different models. And then these are the measurements that I was working with. And what we found is that there's this 20 to 40% offset in the amplitude. And I tried as hard as I could and couldn't get that to fit. So this is what I published in 2016. And since then, I've been working on trying to figure out what's going on. Recently with Johannes Langt, we published this follow-up study where we were looking at the scale dependence and halo mass dependence of this offset. It's using a different lensing data set. But what we basically found is no evidence for any scale dependence or any halo mass dependence. You can see that here because along these different scales, the offset is pretty much the same. And then I'll show you the halo mass dependence soon. So that's a very interesting point to keep in mind when we try to think about what might be causing this. So there's lots of different explanations, and I don't have time today to go through all of them, so I'll just skip some. Modified gravity is a possibility. Given other constraints, it's probably too small for this effect. Massive neutrinos goes in the right direction, but again, that should be less than a 10% effect, so smaller than what we see here. There's baryonic effects, which is the fact that baryons can modify the dark matter distribution. We think that AGN ejects gas from halos, for example, and that this ejected gas changes the potential and sort of pulls the dark matter out again and can change the dark matter distribution. This effect goes in the right direction, but I and others have used simulations, some of which Claude André has been deeply involved in, to see if this could be large enough, but generally speaking, it doesn't have the right scale dependence and to fully explain this. Assembly bias is another effect we've looked at, and here the scale dependence really rules out assembly bias as being a primary explanation. So then you're left with some other explanations. One of the most exciting would be cosmology. I'll talk about that for a few minutes. And then another is systematics, and I'll talk about that very briefly. So the most exciting explanation would be cosmology. And I'm showing here some figures of what the cosmological implications would be. And so for example, these blue curves are where the lensing and clustering tend to want to be. And these are the contours from Planck. And so this sort of shows you the kind of offsets that we might be seeing when we do these combinations with respect to Planck. So this would mean lowering the value of the S8 parameter, could be sigma 8, could be omega m, with respect to the prediction from the Planck satellite. So that would obviously be tremendously exciting if there's evidence for a growth history that is different than predicted from Planck. This is another version of this figure. I'm showing you the same thing. This is from a paper by Johannes. Red is Planck, and these are sort of a compilation of some of the data that we're seeing. Up here is based on the methods that I've been describing, based on galaxy-galaxy lensing and clustering from BOSS. And then down here are some other methods based, for example, the DS, 3x 2 point, the KIDS, etc., and so on and so forth. There's a relationship between the cosmic geo results and the ones that I'm showing here, but they do probe different halo mass ranges, so they could be telling us different things. In terms of the halo mass dependence, I kind of hinted at this earlier. Johannes has divided BOSS galaxies into different galaxy mass ranges and tried to understand whether this amplitude effect has any indication of halo mass dependence. This would be interesting from a theoretical perspective because it could give us some hints as to what could be going on. The 3 bins that we have made are these bins, and we essentially see no evidence for any halo mass dependence here. This is the corresponding range in the power spectrum where we would be finding a low amplitude. So blue and red are basically the range that we probe with this galaxy-galaxy lensing technique. This is the range probed by the CMB. So if the data are correct, and if what we're seeing is indeed what's going on, what would be required is a lowering of the amplitude of the power spectrum on these scales from about 0.1, K of about 0.1 to about 1. So that's really very exciting, and we'll obviously continue to work on that. Another possibility, which needs to be taken very seriously, is also systematics. You've probably heard that lensing is difficult to measure, and it is difficult to measure. So there could be things going on that we haven't thought about. A lot of lensing teams are working on this very hard, whether it's an HSC or DS or kids, or in terms of preparation for LSST. Here's one of the efforts that I've been working on. It's called Lensing Without Borders. I'll be working on this together with Alexie, who's co-leading this effort with me, as well as a number of other people from basically all of the lensing surveys. This was designed to be a collaborative effort between different lensing groups to try to derive empirical methods to test end-to-end systematics. Because one of the things you might worry about in terms of the systematics are the unknown unknowns, the systematics that you don't know about and that you haven't thought about and you haven't estimated. And these are always the trickiest to assess. So we've come up with some methods that enable us to get some handle on this. Oh, it's not totally completely foolproof, but it does give us some handle. So we have unblinded, we have the results. I forgot to tell you, this is basically comparing the amplitude of the lensing signal across all of the different lensing surveys. And the quantity that I measure is a physical quantity. It should be the same independently of the data set that I use. And so we can use this to assess the consistency between the data sets in a completely empirical manner. So we use HyperSupremeCam, the Dark Energy Survey, KIDS, CFHLNs, another survey called CSA2 and Sloan. And we've unblinded the results. It's going through collaboration review, so I can't spill the beans until that's done, but it should be out soon. So that was a cosmology angle where we try to think about the cosmological parameters. But as I mentioned, lensing can also be used to think about questions related to how galaxies form. All right, so I'm going to talk about galaxy size and dark matter halo mass. So you may have heard of the stellar to halo mass relation, which is a relation that tells us about the galaxy mass and its relation to dark matter halo mass. And so here's a figure, for example, on the right, showing halo mass on the x-axis and galaxy mass on the y-axis. And these are some of the measurements that have been made over the years. So this work takes this to a third dimension and tries to understand the connection between galaxy mass, dark matter mass, and galaxy size. And I will mention that we have been focused very much on the very massive galaxy samples, mainly because they are the ones that we also use for cosmology. And so they're the ones that I want to understand in detail to help further our cosmology measurements. And we wanted to ask, do the sizes of very massive galaxies depend on their dark matter environments? So for this, I'm going to use data from the HyperSupremeCam survey, and I'm going to show you a beautiful image of the quality of these data. So this is Sloan, and I'm going to zoom into HSC. And so this is the imaging quality that you get going from a 2.5 meter telescope to an 8 meter telescope. And guess what? You go a lot deeper and get a lot more high signal to noise. These are the data that we use for gravitational lensing measurements. But in addition, there are some other things that we can study. In particular, if you look down here, you see this very massive galaxy. The depth of this data enables us to probe the extended light in these galaxies with really beautiful precision. So this is work led by Song Huang, who's now at Princeton, and he has been studying this for a number of years. This is some postage stamps of some galaxies from these data, rank ordered by how much light we think is in the outskirts. This is a 10 kpc scale, and this is a 100 kpc scale. And we can measure light all the way out to 100 kiloparsecs on an individual galaxy basis without any stacking, which is pretty incredible. And you can see that we've rank ordered these galaxies, and by eye, you can see that there is indeed light out to 100 kpc in these galaxies here. So that's a visual demonstration that we can do what we said we were going to do. To study these galaxies, we have the full light profile. So this is the stellar mass density as a function of R going up to 100 kpc. These are galaxies bin by mass, and these are the average profiles. And then underlying in gray, you have all the individual galaxies. And this is true scatter in the profiles. This is not measurement error. So these galaxies are diverse. Some are very compact, some are less compact, and this is a true scatter. And as you can see from this slide, there are compact galaxies and extended galaxies. But it's easier to sort of summarize this into two quantities. So we chose to use the 100 kpc mass, the total mass of a galaxy within 100 kpc, and the inner mass, the mass within 10 kiloparsecs, really just to make plotting easier. So we can take this and put this on this figure, for example. And when we look at this inner mass versus total mass plane, as I said, these galaxies are diverse. So some live down here, and these are very compact, and some live here, and these are very extended. And there's actually a cloud of data points. These galaxies are not self-similar. They don't live on a straight line. There is a true cloud of data points. So this is a bit like the stellar mass to size plane, because this you could consider the total stellar mass. This is kind of like an estimate of the size. And so the missing quantity now is the halo mass. So to study this, we have made these bins, and I say we, but Song Huang did all the work here. And we step across this plane and we look at the amplitude of this lensing signal. So this is the same signal I showed you earlier. Delta sigma is a function of R. The amplitude relates directly to halo mass, and you can see how halo mass varies across this plane. Whoops. Sorry, pushing in the wrong way. Okay, and so look at this amplitude down here, and you can see by eye the amplitude change. That's the beauty of having new lensing data sets that have incredible constraining power. So what we find with this work is that larger envelopes have larger dark matter halos. And you can see this via this color coding, where this color coding indicates halo mass. So big halos live down here, and small halos live down here. We've confirmed this in a number of ways. We've checked with X-rays, for example. The strongest X-ray detections live down here, and that falls in line with what we find with the lensing. The way we interpret this, and this was partially also aided by studies we did with TNG and Illustris, is that we think massive galaxies form via what's called a two-mode formation scenario, where they form a lot of mass. This is the in situ mass at high redshift, maybe around redshift of 2, where they have a lot of gas coming in. They might have disk instabilities, and they form a lot of mass at high redshift. Further down in redshift, these galaxies get quenched. So there's some quenching mechanism, whether it's AGN or hot halos or combinations thereof, that prevents in situ mass from forming. But they may continue to accrete mass via ex situ star formation. And this ex situ mass could be quite significant, could be more than 50% of the mass today. So if you are a massive galaxy living in a dark matter halo that continued to accrete, so the dark matter halo mass got bigger, you experienced more merging via ex situ mass, and so you now live on this part of the plane. And I forgot to say that the ex situ mass has a tendency to build up the outer envelopes via minor merging. So this is the way that we explain this galaxy halo mass size connection. The next section will be following up on section 2, but thinking about this in a slightly different angle and adding some new measurements. The question we're going to be talking about in section 3 is, how well do galaxies trace halos? What is the scatter between galaxy properties and halo properties? And I'll preface this by talking about DESI. I'll tell you why I'm talking about DESI in a second. But I wanted to say that DESI is a project that the goal of which is to measure the effect of dark energy. And it's going to obtain spectra for 30 million galaxies and quasars over 14,000 square degrees. So it's amazing. And it's the next version of BOSS. It's the first stage 4 dark energy experiment. And right from the beginning, the year one data would be more powerful than the predecessor, which was BOSS. DESI is now in survey validation. So we have data, we're looking at it, that's beautiful. The reason I'm mentioning this is because clusters are an important probe of the growth of structure. So gravitational lensing, galaxy clusters, these are all probes of the growth of structure. And in DESI, we would like to find clusters robustly using imaging and DESI redshifts. And we'd like to avoid any kind of selection effects. And in particular, some of the effects that have come to the forefront in cluster studies, especially with optical cluster finding, are projection effects. So you think you find a cluster, but you're actually seeing two systems along the line of sight. So we'll be thinking about the question of, can we find central galaxies directly? And can we find galaxy properties that have a really low scatter with respect to halo mass so that we can do this cluster finding better and so that we can get better constraints on the growth of structure. So the results that I'm going to show you are going to use what I call the Topend Test. And I'm going to illustrate to you what this Topend Test means. The question that we're really trying to answer is, given some parameter P, does this correlate well with halo mass? So this could be galaxy mass, galaxy size, galaxy color, whatever. So we rank order galaxies by parameter P, and then we take the top N and we measure the lensing signal. And that tells us about halo mass. And then we take a different parameter and we do the same thing, and we rank order again, and we measure the halo mass. Now, if we have a parameter that correlates really well with halo mass, for example, galaxy mass or some other quantity, we will get a very high amplitude. That's because we've preferentially selected out the most massive halos. On the other hand, if we take some property that doesn't correlate at all with halo mass, here I'm giving the example of the time of night when the data were taken, doesn't correlate with halo mass at all, you just get some average halo mass in the universe. And so you have a pretty low amplitude. And so we're going to use this test to try to look at different parameters and see if there are things that correlate well with halo mass. So this is work that's being led by Song Huang and Christopher Bradshaw that hopefully should be coming out soon. And I'm going to take a minute or two to decompose this figure for you. So again, we're looking at delta sigma on the y-axis versus r on the x-axis. And I'm showing you several different quantities. The first one I'll show you in red. So red data points here are from a well-known cluster finder, an optical cluster finder called RedMapper. It's sort of the state of the art in terms of cluster finding with optical data. And this gives you this amplitude. The second thing I want to show you are these light pink points where the subscript is C model. This is a C model luminosity as measured from Sloan. So this is what you get if you go to the Sloan catalog and ask for a C model. And what you find in pink is that the pink data points are definitely lower than the red ones. You see that by eye, you don't need to fit an amplitude. What that tells us is that the Sloan luminosities are a poor tracer of halo mass. And I think that we've had this idea for a number of years. I think we've thought for a long time that galaxy mass is not a great tracer of halo mass, not as good as like a richness, for example, because of the way the luminosities are measured in Sloan. Remember that this is a general pipeline. It's not really tuned to work for massive galaxies. It doesn't deal with extended envelopes because it doesn't fit massive galaxies with the correct profiles. Now, I'm going to show you these other data points here, these blue hexagons here. These are our custom-tailored special measurements of luminosity that are really trying to measure the luminosities of the massive galaxies really well. When we do that, we get an amplitude that is similar to the red points. So what I'm going to show you in the next figure is that that translates into our finding that when you measure the luminosity properly, you actually end up with a good tracer of halo mass, one that is equivalent in terms of scatter to these richness-based cluster finders. One further point that I will make here is that in addition to that, we find that the shape of the lensing signal is better matched. So let's look at these shaded regions. This blue region is the signal that you should get if you did this test on a sample of halos that had 0 scatter. You had a perfect tracer of halos. You did this Topend test. You should see this shape. And this would be something, this is something like an NFW profile. And then out here you have what we call the 2-halo term. It's the structure around halos that you're seeing. And then let's imagine you had a perfect tracer, but with scatter, and with a scatter of some value here. This is the shape that you would see, the gray line. And you can see in this region, the blue data points actually fit the theoretical prediction a lot better than the red data points. And we think that this is due to projection effects. So when you do a red sequence-based cluster finder, you're very subject to projection effects. As you have 2 clusters along the line of sight, you can't really distinguish them with photoz's, even with spex's. And so if you're counting the number of red galaxies, you could be subject to projection effects. And these are expected to induce this kind of signal. However, if we have a method just based on extended light that picks up central galaxies directly, we may be finding halos without or with greatly reduced projection effects. So for a subset of the cluster community, that's really exciting because it takes away one of the systematics, maybe one of the main systematics that has been present. And so this is great. So to turn this into some values for the scatter between galaxy mass and halo mass, I'm going to show you this figure. The x-axis here is the number density. So it's that Topend test. We make bins in number density. And then at the top here, I'm showing you a quantity called lambda, which is a commonly used name for cluster richness with the red mapper cluster catalog. So these are kind of group scale halos. We haven't had the volumes to go to real cluster masses. These are like 10 to the 14 halos. And on the y-axis, I'm showing you sigma, which is a measure of the scatter between a given property and halo mass. And the main thing I want to point out again is the C model magnitude has a high scatter. So not a good tracer of halo mass, but probably just because the luminosities have been poorly measured. Our tracers based on extended envelopes have very low scatter and are comparable with richness. And so we intend to turn this around and try to use this for cluster finding in DESI. So the take-home message here is that with deep enough imaging, we think we may be able to find central galaxies directly via the extended envelopes. And we're working on trying to apply this to cluster finding within the context of the DESI survey. And I'll just briefly mention, it doesn't quite fit in here, so I'm just going to throw it out here. But in terms of studying these massive galaxies, we've also been doing a lot of work doing consistent comparisons between HSC and Illustris and TNG, and sort of using the simulations to try to inform our observations and see how well things match. So we're doing this hand in hand with the measurements. So I'll just refer you to Philippe's paper if you're interested in knowing how the stellar to halo mass relation or how the weak lensing signals compare to something like an Illustris or a TNG. So the final part of this talk is really an advertisement, so it'll be very brief. This is an advertisement for the Marion survey, and the scientific goals that we're going to try to address with these data is, can we measure gravitational lensing for very small galaxies? All of my talk has been focused on very massive things, but this is moving into the low mass regime. So in particular, I'm going to show you this figure on the left of the relationship between galaxy mass and halo mass. This is actually halo velocity, but it's related to halo mass. And as you go down to lower mass galaxies, there are pretty strong disagreements below galaxy mass of about 10 to the 9 solar masses. And 10 to 9 is also the regime where we start to call galaxies dwarf galaxies. And there are differences between what is measured with rotation curves with what is measured with a technique called abundance matching. And there are a number of things going down here. First of all, we think there may be a larger scatter between galaxy properties and halo mass. This also ties in with the cusp versus core problem. So the fact that dwarfs have a range of rotation curves, perhaps related to baryonic effects, could be signs of dark matter. A lot of questions to be unpacked in this mass regime. One of the difficulties here is that we don't really have good traces of halo mass. We have rotation curves which probe the inner part of the halo. We don't have measurements for dwarfs of the full halo mass. So when we say that we disagree with lambda CDM or that things like that, we got to keep in mind we actually haven't measured the full halo masses for galaxies in this mass range. So we set out to try to see if we could push gravitational lensing down the mass function, specifically targeting the range 10 to the 8, 10 to the 9. And here's a prediction on the right of a prediction of what we could measure with like a fiducial HSC survey. So I wrote this paper as sort of a investigation of whether this could be done. So from the statistical point of view, like, do we have the lensing data sets to do this? Now, what I found is yes, and HSC will be able to do this. LSSD will be able to do this really, really well with signal to noise of like 200 or something. However, even though we have we will have the lensing power to do this, finding a sample of dwarfs and getting redshifts for them is an entirely different beast. So hence the Marion survey. These are some of my collaborators down here. This is work I've been doing in particular with Jenny Green and her group. And we named this after a 17th century scientist called Marion. And she was the first entomologist and naturalist. And we named it after her for two reasons. One, because she studied very small things. She studied insects, and we're going to study these really small dwarfs. So we like that analogy. And secondly, she had amazing observational skills. When she was alive, people didn't necessarily think a great deal about observing the world. People preferred to go and see what the Greeks had to say about things. But she had this great idea, let's look out and see what's going on. So she actually collected insects and studied what happened to them, which was quite revolutionary at the time. And she discovered, for example, just by having a collection of caterpillars, that caterpillars turned into butterflies. So this metamorphosis was unknown at the time. People thought that butterflies transformed from pieces of dirt. Pieces of dirt would randomly turn into butterflies, was what people thought. So we really like this analogy of observational skills, and we're going to try to be as astute as she was in this work. So this is our namesake. And then what we're doing is we've designed two custom-made filters. These are medium band filters that will target the H-alpha and O3 emission lines of dwarfs in a narrow window of about 0.05 to 0.09. And we have time approved. We're starting, I said January, but we're actually starting in March. We have 60 nights on the Blanco telescope to survey 800 square degrees. We think we're going to find about 100,000 dwarf galaxies between 10 to the 8 and 10 to the 9 with pretty good redshifts, because we will pin them down to the range 0.08, 0.09. So much, much better than anything we could do with a photo Z. Not a spectroscopic redshift, but it would be incredibly hard to do this with spec Cs. It would be impossible. So with 100,000 dwarfs, we will be able to measure the gravitational lensing. And there is a ton of ancillary science that we can do. And also this will be a learning period for how to do this kind of narrowband science for the ribbon project. So I will stop there. And next time, hopefully I can show you some results from Marion. But in the meantime, here's my summary, and thank you for inviting me to speak here today.